All right, hit record, then I'm going to share my screen here. And then make sure that, okay, Zoom's still working. All right, and then we'll just hit share on this. How are we? Can we see my screen? All right, getting the thumbs up. Awesome. So the sort of uh initiation of all this is that I've been thinking a lot about standards lately. And it felt like, okay, this time let's just talk in a sort of a general way. A lot of times we do kind of like a show and tell here. Um, and just because I had read a bunch of these standards papers, I was like, you know what, let's put it all out there. And also I wrote one of them, which probably also helped initiate the whole thing. Um, I don't know how, let's see. Did anybody get a chance to flip through any of these? It's cool if not, but put up your hand if you had a chance to glance at anything. Okay, cool. So I understand what we're working with. Um, so uh, basically, this is like a literature review. I'm just talking about three things, and we'll talk about the ups and downs. It's really hard to put a sort of a standards white paper into a compelling PowerPoint. Um, and so the way I did it is that I just said, well, here's some big points, and we can talk about those. But along the way, feel free to just jump right in if you have thoughts or questions. Um, I kind of went through this last night and was like, there's like 30 minutes of content in here. Um, and so I think we're just going to breeze through stuff. A lot of it washes over, but feel free to jump in anytime and ask a question. And I'll just make sure we do at least see the last slide. But we may not really cover everything. It may be quite uneven if people are particularly interested in one thing, because this is fairly wide ranging. All right, so that given, here's just three proposals that came out recently about automation integration. Before I get started, I just wanted to make sure everybody's on the same page of what integration is. It is sort of a broad term, but here, just for this talk, it's putting together two pieces of automation so they can carry out a complete automated workflow. So you've got some automated thing, and you need to plug it into some other automated thing so that the entire thing gets done. So maybe it's a liquid handler and a plate reader, and they're two different pieces of equipment, and I just want to automatically measure a bunch of, or prepare a bunch of liquid samples and then put them on a plate reader. Well, those things need to be plugged in. All right, just making sure that we're all understanding what we're saying with integration. The other thing I wanted to split out here is that a lot of times in Open Auto Club, we talk about automation, and it's kind of oriented towards lab automation. So a very sort of particular sort of liquid handling sort of automation. But I wanted to sort of float out two different styles of automation here, because these papers kind of cover both. So on the left is what I'm going to call control systems automation. There's a bunch of things you could call this, but just sort of broadly, it's a focus on a bulk process, so something like a big tank. In this diagram, there's a tank that we want to have a consistent level on. So I have liquid flowing in and liquid flowing out, and I just want to make sure the level is always the same. This is often done with feedback-oriented control. So there's something where, in this case, we're measuring the level of the tank, and then that measurement goes into some kind of computer, like an embedded system. This is a PLC, a programmable logic controller. And then that does some math to figure out how open should this valve be to change the flow rate. And you end up with a lot of these charts here that kind of say, I have a set point, this SP, and then my PV, or process value, needs to raise, I want to get my PV to equal my SP as quickly as possible. And so like what this looks like in an implementation level is often just a lot of networking. You have sensors, actuators, and you need to network them all together. But we're not really concerned with like 3D space. Most of our concern here is about making sure that these wiggly lines become straight lines. So that's kind of one whole world of automation. My background probably has a little more to do with that than the second part, which is mostly, I think, where we sort of land, because it makes more sense on smaller scale, is robotic automation. And here, just to bullet point it out, I said, well, there's a lot more focus on like piecework, like there's an individual sample or there's an individual piece that I need to move or assemble. And that means that we do a lot more 3D motion. We have to understand 3D space much more. And then often the way that we do this is that we say, well, I have a single robot, but in fact, I need to integrate it with many things. And so it talks to, as you get bigger and bigger, you need to have it talk to some sort of orchestration service so that two robots can work together or a device can be utilized. And we'll get into that. But I just wanted to sort of lay these two out because these papers kind of go in and out of both of them. All right. So let's jump into Bioforum. So I thought this was a really neat paper, and it was one of the reasons that sort of instigated putting all of this together, because it just happens to speak to a lot of my passions professionally, which is that this group Bioform is a consortium of mostly biopharmaceutical, and in fact, a lot of these things kind of come out of biopharmaceutical thinking. Um, and I think that's just because, as most of the people on this call know, working in the industry, not everybody, there is a lot of there's a lot of need for automation because of this sort of the way that biology is very complex, but also needs these really large search spaces. So you have to just do a lot of repetitive things. Um, and so the complexity is sort of their first point. They say, hey, biopharma systems are super complicated. The biology is complicated and the system is complicated. So it's really crucial because these are medicines that we reduce risk everywhere. So no matter what we're doing, we should just say we have the minimum risk of something going wrong. They then say, oh, well, buying stuff off the shelf is actually great for us because it arrives faster and it's already been validated because it's been used a million times. You know, you don't expect your, if you buy an iPhone, which is mass produced, you don't say, oh yeah, one out of every three will just break and not work, right? You get a much higher success rate with off the shelf parts. But they say we don't have standard control software for all this stuff. And that increases the risk, and we don't like that. So we want to figure out a way to get an off-the-shelf model where we can just sort of buy automation tools and integrate them in a way that just is like Legos. I just, plug them together, and they call this plug and play. The kinds of softwares that they want is sort of everything at multiple layers. So they want to be able to automate their process, but also like directly control, like how open should this valve be? So there's like an electrical signal going onto a wire. And they want to provide operator interfaces. So now there's like a UI to this on top of everything else. And they would like all of this to sort of just click together. The core way that they talk about doing this is they basically say there's two things: a process equipment assembly and a process orchestration layer. So they just abbreviate these. So it's a P and a pole, which I think is fun. The P is an assembly of equipment carrying out a specific process step. So this is very like chemical engineer thinking. But to put something more concrete to it, this is a bioreactor on the right. And you can see here that, sure, there's a tank, that's the bioreactor, but we also have a control unit, and this is a scale down here, and there's a condenser. So there's sort of various parts, and all that together is the thing that does the fermentation. And so we call all of this together the P. And then they say, and then there should be something hierarchically above that, and we'll look at the diagram in a minute, that orchestrates all these P's together. So you should be able to sort of start with these kind of lower level pieces and then say, okay, but the bioreactor needs to interface with, oh, I don't know, let's just say a centrifuge, or maybe a special tank that feeds carbon into it. And so those all kind of work at an orchestration layer. Their goal for this, because they are industry professionals who say, yeah, well, we should still have jobs, is that, and also I think this is realistic. I mean, 80% of typical processes for each equipment class work. So there should be these sort of packages that say 80% of anything you would do with a bioreactor. It's out of the box. Just call the ferment button or method or something. But they also admit that 20% of it, yeah, you're just going to have to do custom work on this. So you're still going to have to get into the software and change things. But they want you to kind of get a starting point, which makes sense to me. Okay, let's look at the diagram. This is probably this is the big meat of this. I will recommend it if any of these look interesting to you, do pull them out, because this one especially has a lot of sort of very white papery talk about, like, here's how you should think about IT security in our framework. And so it's trying to give a very high level treatment. It doesn't give all the answers, but it's trying to just be like, hey, automation professional, here's everything you might have to think about on this. So the way that they do this is we've got, P number 1 from vendor X, and then there's P number 2, and then there's another P number 1. So maybe it's just the same piece of equipment, but it's from a different vendor. And when we plug these in, so we start to set these up for the first time, First, a configuration process happens where we have to link them to this higher level software, the POL, the process orchestration layer. Um, and the Ps send a file called an MTP file that describes their own capabilities. So it's, I actually don't know that much about the specification. But has anyone heard of an MTP file? Is this, okay, I'm not seeing much. Uh, yeah, apparently it is a slightly older standard. It's not totally brand new, but it describes the capabilities. So the P can say, yeah, hey, I'm a, let's say it's a bioreactor, and the commands I have are, stir, feed, harvest, and maybe cool. I don't know. We're picking some, right? But they basically give the handles. So it's almost like, here's how I want you to talk to me, Paul. Um, and those all sort of work on a specific specification. So there's sort of a set of primitives, and then you say, given those, you can send me the following commands, and I will accept them. And this is all sort of written up actually. They marry a handful of other existing standards. So there's a bunch of European standards, and then in America we have ISA, which also does some of this stuff. I mean, ISA is international, but I don't know. I hear it less other places. Okay, so once we've configured it, now we've done that, and the process orchestration layer theoretically knows what it needs to know to be the sort of commander of the whole system. And during runtime, the POL sends the P service command. So here, do the following based on some internal logic that it has, and then it also sends things like recipe parameters. So maybe it's something like, hey, yeah, I want you to run your cooling system, and the temperature it needs to go to is 20 degrees or 30 degrees, and it can change that during runtime. And then vice versa, the P is sending back up to the POL process values. So like, what temperature is it? And then things like equipment status and alarms. One of the things I thought was sort of interesting here is that they make a point of saying you should do as much of the interaction at the POL layer. The P just sort of listens. But the safety stuff belongs as low as possible, which I think makes a lot of sense. A handful of other details here. So basically, yeah, so the italics here are quotes. So once a P has been plugged into a POL, the primary operation of the P shall be performed through the POL. And so this is this idea that like, no. Like if we go back actually, let me go back to here, you can see that this bioreactor has a screen on it. And that's very common, right? When you get these pieces of equipment, they have their own interfaces. But what they're saying here is that screen should be purely decorative, or maybe it can have some status, but you shouldn't really interact with it unless there's like a crucial safety thing. Additionally, they then say that services built into the P can range from low-level equipment functions to complex sequences. I also thought this was interesting because what it's saying is, yes, it could be something like cool, or it could be, hey, here's an entire recipe I want you to run. I'm just going to send you the command. And if the P knows how to carry that out, if it's sort of pre-programmed with that method, then it can theoretically do it. I sort of wonder if that's too open. For me, I would start to feel like, oh, I don't want to give a robot like a 2-hour protocol without any check-ins. So I don't know. The implementation on that seems interesting to me. And then this isn't a direct quote, but I'm sort of paraphrasing that standard data connectivity validates faster and provides higher quality data. And this is one of their compelling points as being in biopharma, validation is so important. So you have to, from a regulatory perspective, be able to say, yes, I am proving that this thing does the same thing in the same way every time, and thus the product is safe. And what they're trying to say here is that if you do all your data in a standardized way, so if I go back to my architecture, you can see the POL is actually sending all of this data that's in green that should be coming up standardized up to, they say, other OT platforms or OT operational technology. Like a data historian. So you're tracking all of this data. And the compelling thing that they say in the paper is that if that data is getting into that database in a consistent way across all users of this standard, then it actually gets much easier to validate. And that's true both internally, so you can prove to yourself that this works, but also with, I mean, from their point of view, the FDA. But I actually think it's also useful in transfer if you're just working with somebody else, whether it's open source or not. If everyone's on the same sort of data standard, you go, oh, yes, I see how this is supposed to work, and it's easier to plug in. And then I'll just shout out a couple of the suggested technologies. This is pretty high level, so they don't say the spec is this, use the following, but they say we think MTP is the right file type to talk about capabilities. They emphasize OPC UA to encode data and control messages. Are people familiar with OPC? Anybody? I see a couple of nods. All right, some shakes heads, some nods. Um, and yeah, Luis, I assume that's a yes. I'm familiar with OPC. Um, so yeah, OPC is it's just a communication standard, but I've been seeing it more and more become standardized in like pretty much across scientific and manufacturing pipelines in the sort of the biospace. It works. It's good. I like it. I always tell people it has a sort of like evil little brother called OPCDA. Never use that. Um, it's married to the Windows kernel, and so you have all these weird configuration problems. But OPC UA is good. So I buy it. And then finally, for transport layer, they say Ethernet IP. IP in this case is industrial protocol. So it's Ethernet plus this sort of extra layer of robustness that gets put in place to support industrial processes. So yeah, that was interesting to me. OPC UA LADs. Oh, interesting. That actually comes up in the next paper. So we should yeah, we should talk about that. Um, and thanks for putting that link in the chat. All right, any thoughts on that? I think we're doing all right on time. Any sort of questions on the bioforum stuff? This is, I think, the most important part of the whole piece. All right, let's get into the next one then. Okay, this one is lab automation plug and play. I got sent this paper by somebody who saw my blog post actually and was like, "Hey, did you think about this?" And the answer is no, I hadn't thought about some of the stuff they have here. And this one, unlike so the Bioform stuff is very oriented towards what I was calling control systems automation. Um, this one is a lot more like, hey, you have like a lab somewhere and it's sort of built for humans, but you think you need to automate it. But you have all these devices everywhere and like you're not on conveyor belts. Like, what do you do? So I thought this was neat. So basically what they say, every paper has to talk about like, why did I spend 2 years on this? And what they're saying is, well, it's getting harder to discover new drug targets. The low-hanging fruit's gone. It's hard to discover things. Additionally, reproducibility is a real challenge, especially in academic environments. So it would be good to automate more because automation both lets you explore larger spaces to discover more things and do that reproducibly, at least in theory. But what they say is the particular requirements of biopharmaceuticals make it challenging to adapt cutting-edge technologies present in under other industries. So they are laughing at us in biology and saying, hey, other industries are figuring stuff out, but your system is too complicated or something. So they specifically cite there aren't enough standards, and then it's sort of laughable. They go on to name every part of the process here. It's like, well, the devices, the data, the materials, the consumables, the interface, and the regulations, none of it's standardized enough. And so I think, you could just have a whole conversation about that. Which of these is the real hot spots and what are the issues? Because I think, there are regulations, but they have a point there. And then they also say there's high integration effort required for both the integrator, so somebody who's like, an automation person trying to get a robot in place, but also the user has to adapt their workflows into the automation. And that's painful as well. They also add in mixing conformity with GXP. People familiar with GXP? In short, there's good laboratory practice, good clinical practice, good manufacturing practice. These are all terms from biopharmaceuticals, and they all just mean roughly you should have a really good audit trail. You should say what you're going to do. You should do that. You should record the fact that you did it, and all of that should be packaged in a way that you can find it later. And so what they're saying is that automation, if it's done in this sort of like duct tape sort of slapdash way, often doesn't conform with that because you don't have good records. They also cite IT security concerns. Hey, you're plugging stuff into the internet. Uh-oh, that could be a problem. Limited robot adaptability. So robots themselves don't necessarily plug into an existing lab very well. And then reverse of that is say, I have a device and it's just not ready to work with a robot. Maybe it has a lid that is hard to manipulate by a robot, even though a human can do it really easily. So if devices aren't built with robots in mind, that's a challenge. So how do they try to solve that? Well, they basically imagine that you're going to use a mobile manipulator robot. So like this cute little guy. Um, so he's got little wheels, and then he has, in this case, two manipulators. They seem to like two manipulators, but you could do one. And their claim on this is that there's too much. It's too idiosyncratic. All these different instruments. And so they say, well, if you just get a robot, it solves a handful of problems. One, material movement is challenging in automation, at least in a lab context, because it's pretty trivial for a human to take something out of the freezer and then walk it over to a different lab and then say, okay, I'm going to do my preparation here at this bench, but then I'm going to pick up my sample and go to a different bench. And that's like a huge problem for robotics, actually. And so what they say is, well, cool, let's just get sort of human-like robots, and they say run them like cobots, which is to say it's in a mixed environment where humans also exist. So the environment has to be friendly for both things, and also the robot needs to figure out how to recover if a human moves through in an unpredictable way, both for its own sake, but also to like, not crush the human. There's definitely automation environments where you just assume humans will never be there, and so you can say, oh, here's a big crusher, and that's not true with these guys. They need to be able to, oh, I bumped into you, I'm sorry. Um, and uh, and so they say use that, and then they say, well, that's not enough. And they say, what you need to do then is to make this cobot work with everything. Is you need to put two stickers on every device you want it to use. So they're picturing kind of like a human lab, and the two stickers are the first one is a 1 or 2D barcode for referencing device information. So it's like a QR code. And the robot's going to use, it's got little cameras here, and it's going to use that to look up how to interact with this device. So this is kind of equivalent to the MTP file in Bioform's plug and play protocol. The way they envision this is that the robot scans this, and then it is able to, it's configured to talk to some database. And they mention a few database possibilities, nothing that I'd ever heard of, but worth digging into maybe if this is compelling. And on the next slide, I have some information or some details about what kind of information they would find. But basically, it's like, hey, I'm a plate reader. This is how you should talk to me. Uh, the second sticker is a fiducial marker for pose detection. Anybody familiar with fiducial markers? I'm not even sure I'm pronouncing it right, to be totally honest. Okay, I saw some nods, some shakes hands. It's really interesting to see. I feel like we get like switched experiences, which is great. It means we're all learning. So a fiducial marker it's like those little stickers that I see them, definitely in automation spaces. I didn't know what they were called, but they are for cameras and robots to figure out where they are in space. So if they're orienting themselves. So if you put this marker in a specific space, the robot can find it and it can update its own model to be like, this space is here and this is the angle I'm at. I can tell because of the way the blocks are assembled. So it sounds a lot like when you do like CGI and like those mocap suits and stuff. There's a similar sort of concept going on where the robot's figuring out how to orient itself. Okay. The data that we would get from the first barcode, they give a handful of examples here, but you can see it's stuff like basic information about what am I working with? Okay, this is a plate handle or a plate reader. It's made by TCAN. I know how to learn stuff about TCAN. But also things like they've got this device features written down, e.g. Scylla. And Scylla, are people familiar with Scylla? There's so much sort of background in here, but okay, got some nods. This, like I promised you, this was just going to be like, here's a wash of different ideas. Scylla is a lab automation standard. I actually haven't used it. I don't know if it makes people happy or not, if it's a positive thing. I do actually think it would be interesting to dig into. I'm just not that familiar. But basically, it's a standard for saying how to control something in the lab automation space. And so if this device, my robot looks it up and says, oh, you're Scylla compliant. Cool. I know the handles that I have to talk to you now, or the way I need to talk to you. So then it initiates a communication process. And then they also talk about things like you can see here on the right, they talk about like digital twin of the device. And so there's also like a sort of pure software component, like this has to go talk to something else. So this is your Rosetta Stone, right? As soon as you scan that thing, then you're going to get a ton more information as the robot about how to interact with this. So this is how they envision it. I love their diagram. It goes like this. It's a simple 10-point system. First, And this is what I was really appreciating about this paper is that first thing it has to do is this is a robot that needs to move in 3D human accessible space. So it needs to constantly update a map of the lab, like it's a self-driving car. Um, so first it does that. It figures out where am I? What am I doing? And then it figures out how to get, roughly where it needs to be, at which point it detects the barcode. And it says, this device, this plate reader, I found its barcode. I'm going to scan that. Aha, I am learning everything about the device I'm near. And then it detects the fiducial pose. And it says, okay, cool. And this is how I position myself against it. So we've done two levels of location finding now. First, we've done the gross location finding, which is I have a map. I'm going to figure out how to navigate pretty close to this device. And then the fiducial pose lets me do slightly more precise. It was interesting. They gave some precision levels for different automation systems, and they were saying that like this kind of mobile manipulator, it's like 50 centimeters is really the best it can do without some help, which is like bad, right? Like that's unacceptable. But this is why you have this like fiducial code. Um, so at this point, it says, cool, I have scanned the thing I'm using, and then it imagines we're going to go talk to in sort of yellowish here. They have this thing called a scheduler. So this is something that's sort of managing like what's the current state of everything. They give an example of this software called Unite Flow. I don't know if this is an Austrian thing or not, but basically, these sort of scheduling tools. It sounds like MES would be maybe a term I would use, a manufacturing execution system. But the idea here is this thing is keeping track of like, is this thing available? Can I block off its time, this device? So at this point, the robot's saying, cool, can I use this device? I'm ready to use it. Hey, if it is available, nice. I'm going to use it for the next hour for some protocol. And so the scheduler can keep track of all of that. Then it gets all the information to understand how to interact with this. Let's say it's a plate reader. It spins up a digital twin from the cloud database. And so that it can be sort of modeling like, I'm not totally clear about whether they mean a physical digital twin. So like I am understanding whether or not this plate reader has its tray open, which is important. But then there's also the second part of like, you might be interested in tracking the interior behavior of the system. So it could be, well, this thing needs X amount of time to read things. Well, that's useful to sort of model out. Or it could be something more complex, like if we were going all the way to a bioreactor, I could imagine, well, there's a complex chemical reaction happening there. Maybe I want to model that. Then it's, the digital twin is a long-running process. At which point, okay, now I've done all of the basics of like, I've configured everything. It's as simple as, great, now through this network system, I'm going to tell the device, let's say, open the tray, and then the robot goes, cool, I'm going to manipulate, I know my positioning in 3D space, and I'm going to tell the robot to drive to a specific spot and put whatever my sample is into the tray, and then, update until done. I thought I had another slide on that. Oh, well. Yeah, so this thing, I think the thing that really stuck out to me here was sort of the realization that like you both need to keep track of what to do in a sort of like device level way of this device just, hey, I can open trays or I can take readings or something. But you also need to talk about where to do it in all this automation, which is not a way I'd quite framed it before. So in a lot of ways, this LAP protocol is trying to solve the where to do it problem, because it basically relies on something like Scylla to say, yeah, this is how you can tell a plate reader to open or a liquid handler to aspirate or something. And then what this is saying is like, I'm going to try to solve the 3D space problem through a series of cameras and databases. Any thoughts or questions on that before I jump to the last one?
I wonder if there's actually a case where you might want to have two robots, and like one's just supplying reagents or whatever to the different systems, and the other one's actually moving the pipeline of the experiment through the system. So they'd have to talk to each other as well. So a higher level.
Yeah, no, it's a good point. I mean, they basically, what they talk about in this paper is they mostly imagine a robot plus humans, but I think the implication is, yeah, you could have many robots. They do cite that robots like this, these mobile manipulators, they're not that fast. Like it's much faster to do an in-place robot. But these guys can work 24/7. And so they sort of make up for their lack of speed by just working all the time. So I think you could imagine, yeah, just like full of multiple robots. I'm not totally clear, and I think the details of the scheduler end up being what's really important there. Like, is the schedule really only scheduling devices, or does it also somehow keep track of all the robots and their schedule? Um, I suspect the self-driving car industry has a lot of thoughts on this. All right, so we'll go to the last one. Um, so this is a blog post that I wrote a couple of months ago. This came out of this NSF Pose workshop, so Pathways to Open Source Ecosystems, where we were talking about how do we create ways for open source communities to exist inside of automation. Um, and obviously, I said, come talk to my friends at Open Auto Club. But the sort of theory that came out of this was like, hey, there's actually a lot of tooling already, and many people are working on projects. But how do we sort of collaborate? And we want to like be able to integrate with each other better. One of the big wins of that was someone brought a pipette and plugged it into someone else's sort of CNC machine to make a liquid handling robot. Um, but the thought was like, how do you do that at scale? And so my sort of take on this was, well, if we want to do novel science, we almost definitely need to customize our own automation because there's too many very specific things we want to do that are unpredictable in a usual automation workflow, especially in a university sense. Like if you're at NSF level of like, oh, I'm working very, early stage scientific, there's just gonna be customization. And in order to not accidentally spend your PhD becoming an automation engineer, although you could do worse, you should probably figure out some way to collaborate so that you can save resources and share resources. Okay, in order to do that, I'm saying that, well, you need a way to execute scientific experiments in a really specific high context environment. So this is like, yeah, okay, but literally what coordinate do I need to move my liquid handler to in order to get the, well C6 on plate 3? Right. So this is like highly specific. You need to know the material. You need to know the container type, stuff that humans just don't worry about because it's sort of implied. At the same time, you need to keep the scientific ideas in those experiments in a general shareable form so that you can actually, create insight. So that was the idea, and that led me to this. So my sort of core idea is the way to get here is to abstract the layers of software so that we get clear responsibilities in each of these layers. So one of my, constant frustrations with automation is that we have a lot of software that doesn't have a clear responsibility. And, the tendency that I see is that people write a lot of software that or they create a lot of software products, right? So something that is for sale, and it covers 80% of use cases, like of everything in all of these circles, 80% of it is covered, which is not enough. I would like to see either full coverage would be great, but then you're but the truth is that it's kind of hard to do full coverage unless you're customizing every single thing. So so we end up in this sort of like middle zone where like, a system is claiming to do 4 of these, but not everything, and it becomes hard to integrate. Yeah, good point. 80% coverage, 80% coverage actually would be pretty good. I think my frustration is that they don't stay within these boxes, but they also don't cover everything. So I want one or the other, and my proposal is, okay, great. Let's just all be really clear about which kind of software, which module we're covering here. So I'll just go through these. So I wrote this all up. With little annotations, and I go into much more detail in the blog and try to work through a few examples. But this is all pretty high level. And what I'm saying is, okay, we start with a workflow definition. So this is a domain-specific language that defines an automation protocol. I think there's actually a handful of these that exist, and it probably just needs, a little bit of tweaking to sort of work within an entire system. But this is just a written text-based way to write out a protocol. I want to do the following. The crucial parts about it are that it has to be text-based so that it's human readable. It's not a binary, and it's open format. And then also it's storable in a data system. So you can put it in a repository so people can come grab it, or put it in a database so you can reference it. Oh, this was the protocol that got done. My idea here is that composability is especially great because you want to be able to say some fundamental primitive, like, I don't know, let's just say aspirate, right? So pull up a liquid, but then you could compose it and say, well, a distribution across a row is when I aspirate a certain amount and then distribute an equal amount of liquid all the way across those rows. So I can combine different methods. Okay, so given that, once I have written this part out, I send it to what I'm calling the command layer. And this is something that allows agents to start, stop, or update a protocol. It's the touch point to this entire system. I say agents because it could be a human using a UI, but I think if you do it right, it could also be another computer, some other process talking to this automation system. Which becomes sort of crucial if you're saying, yeah, I want to do like a self-driving lab. I want to do some additional work that closes the loop or that kicks off automation from some remote system I don't have control over. You could provide your API here. So what I'm saying is, when I send my workflow definition to this command layer, the command layer first says, hey, I'm going to try to simulate this. And to do that, it says, well, okay, actually it talks to the execution layer quickly and it says, hey, what devices exist in this lab? What do I have sort of control over? So the execution layer, its job is to sort of retain the right now state of the system. So this is equivalent to the sort of scheduler that we saw in lab. Um, and I'll move faster. I realize we're quite close to the end. So here, this is going to say, okay, well, here's the devices I have. Here's their capabilities. This is where everything gets registered. Then we come back and we simulate and say, oh, it is possible to do this workflow. The devices have reported they're able to do this. The simulation could also do much more complex things. Like I was saying, like a chemical reactor, you could say, I'm also keeping up to date to figure out if I need to update my controls or something. Then if everything looks good, the execution layer is going to then kick off an orchestration process. So this is a long-running software process. So it's virtual and it's running on a loop. And this thing's job is to keep track of everything in real time and make sure that all the devices are sort of humming together as one big system. The orchestration layer then talks to what I've called a meta device, which is really just a convenience layer to group several devices, where devices are the actual sensor or actuator or some sort of physical system. And then the meta device just lets you collect a few of those together and say, actually, I'm going to integrate these in a more traditional way, but the meta device is the actual connection point to the orchestration. It's the one that complies to the standard. And so it handles the messages that way. All of this comes down into logging. So the orchestration layer is responsible for keeping track of everything coming from these devices, like we saw in the Bioform plug and play. And then it generates this log. And the log is really important because my sort of thesis on all of this is that, like in the Bioform case, if you have this log and it is generated in a standard way, here's everything that's happened. Here's all the sort of low-level operational information I have. You can then compare it to the workflow definition file, and you can do automated checks on, did this work the way I thought it would work? So kind of like we talked about validation earlier, we could also say that it's easier to share things, and in fact, easier to do scientific insight from this. I'll zip along. Yeah, I can skip most of this, but my highlights here are devices have to report their capabilities, and that has to be a standard lexicon. How much logging is too much logging, Nico? But that's a great question. I think we should work that out. But yeah, so and then I was saying I think we should pair this with some sort of physical integration standard, and that could be something like LAP, which does positioning, but also like literally I want to click two pieces together. If we're going to say this is like open source and scalable, then we have to have something for that. I'll skip my technologies because I don't actually have any firm ideas, but there's some stuff to think about there. Summarizing, Bioforum, their basic approach is say, unify everything up to a central orchestration tool. LAP's solution is automate existing devices with cobots and try to make like smart environments. And then DIP, my sort of idea is that like this could be, you build an interchangeable software ecosystem. And we can build that sort of ground up if you know these sort of general modules make sense to people. Yeah, and here's my here's my takeaway. Um, I think all of these basically point us to there are a lot of ways to think about automation and automation integration. And I really think all of these are valid and there's good parts in all of them. So I think something to think about, coming out of this is, okay, what's useful here? And then, what fits most closely. And with that, I will stop the recording. Uh, and we can chat for a minute or two before the end of the call. So thank you so much.